In this video, we're going to talk about integration by substitution. So in the past, I would ask you to integrate something like this. And the way we would do it would be for us to think of something in such a way that when we differentiate it, it would give us this. And the way we would do it would be for us to zoom into this bit, and then we would make this to be our initial guess. So our initial guess would be something like this, x to the power 4. So this would be our initial guess. So we would imagine this as being in a bubble here. So when we differentiate this, it would then give us negative sine x to the power 4, and then we got to times with the derivative of the bubble itself. It's really us using the chain rule. So this would give us 4x to the power 3, and then when you tidy this up, it would be negative 4x to the power 3 sine x to the power 4. You see, this here is x to the power 3. This is x to the power 3. So we would then make the adjustment to our initial guess. So we need to get rid of this negative here. So we would need to make the adjustment to our initial guess. So we would need to stick a negative in front of it. So now when you differentiate this, it will give you this, but without the negative here. Now we need to make the adjustment. We need to change this 4 to a 2. So make the adjustment to our initial guess. So this would be our adjustment here. So now when you differentiate this, it would give you this. So this has been our normal routine of integrating this. But now I need to show you the formal way of doing it, because if it's nice and simple, we can just use our normal method and just jump to the answer. But if I were to give you something like this, you won't be able to just do it in your head and just jump to the answer. You see, this here would be quite difficult for you to do in your head. So we now need to, if I were to give you this is quite easy. We can just make our initial guess and then somehow get to the answer. But then for us to do this, we would need to use substitution. It would be a lot easier to use substitution to do this. So now we are going to look at the formal way of doing it. Okay, so if I were to ask you to integrate this, hang on. So if I were to ask you to integrate this, your eyes would usually zoom into this bit here, and then visualize this as being in a bubble. So the way our old method of doing this would be for us to make this to be our initial guess. But now the new way of doing it would be for us to say let u equals x to the power 4. Okay, and then later on we can do this. Then cos of u. Then now we can put the u into this thing here. So this thing here becomes a lot simpler. Okay, so hang on. So if I were to ask you to integrate this, then you would say, well, your eyes should zoom into this bit here and visualize this as being in a bubble here. So you would say let u equals x to the power of 4. Well, if u equals x to the power 4, then you can say du equals 4x to the power 3 dx. And you by now you should be comfortable with this du on this side and dx on this side. You should be comfortable with this. From our section on linear approximation, we've done a lot of this here. Well, if looking at this here, if I were to say to you y equals x to the power 4, then you're comfortable with dy by dx equals 4x to the power 3. But then from our section on linear approximation, we can treat this as one being. We can treat this as one being. So you can then multiply dx to both sides. So that would give you this. So hopefully that you can see why you're able to jump from here to here. Okay. Or another way of looking at it is, suppose you have a graph here. Let's say y equals in this case it's u equals x to the power 4. Well, then let's say this is our right angle here. So this is our du here, and this is our our dx here. This is our dx here. So you're comfortable with the true gradient is du by dx equals equals 4x to the power 3. You're comfortable with this. So you can multiply this to this side here. So what it's saying here, this thing here, what it's saying is that, well, you can imagine the height. If you want to know the height here, then you can just get dx here and times the true gradient being this. And then, well, when you look at this statement here, it's saying if you want to know the du here, which is the infinitesimally small height here, then you can just get dx and then times with the true gradient, which is 4x to the power 3. Just bear in mind that this du here is smaller than delta u. This dx here is smaller than delta x. So when from here, if you moved into the realm of limits, then you would get dx here. This du here, if you move into the realm of limits, then it becomes du. Well, we've done this many times in the past. So from here, we can jump to here, and then hang on, and then let me think, and then dx equals this thing here. So we can now put this. We can put this into. Looking at this, this is the same as this. So we can actually put the u into here. So this thing here is really sine u, okay, and then well, notice that this is the same as this dx here. So we can put this into here. So this would then this thing here would become this, okay. This thing here would become this, and then this would cancel out with this thing here. So that would then give you this. This is a constant. Take it out. Then that would give you this. Now this is quite easy to integrate with respect to u here. So it's nice and simple now. So that would then give you this, okay, and then this then becomes this. But then remember from above we said u equals x to the power 4. So now we can put this thing into here. So that would then become this. So this is pretty much the same. Well, this is a formal way of doing it, because I know in this case it's nice and simple. We can just use our old method and just jump to the answer. But later on things will become more complicated, so we need to take it step by step. Use substitution. So let this equals this, and then we can translate this into this, which tidies itself up into this. You see, once it's in this form here, it's nice and simple to integrate. Okay, so from yeah, okay.